Our next speaker is Dr. Grigor Sievers. He's manager in the Electrical Services Department at D-PHYS, and he will be presenting how to engage in a data-driven development and testing using MIPI automotive sensor interfaces. As a reminder, we will have a live Q&A at the end of this presentation. You can use the chat feature in the panel on the right-hand side, and we'll try to answer as many questions as we can. And Grigor, please take it away. Thanks.
Yeah, thanks a lot for the nice introduction. Just start with a short agenda. So my talk will start with autonomous driving and some challenges we see in the industry here, and then I will present data-driven development. So the different steps that we see here. So starting with the data logging, data ingestion, the management of data, the labeling of data, and last topic here is the data replay and the testing. But let's start with the challenges. So autonomous driving has for sure a lot of challenges, technical, governmental, whatever. But one really important thing here is that we have to ensure the safety of an autonomous car or autonomous vehicle under all conditions. This means different weather conditions, on a motorway, in an urban area. So we really have to ensure the safety here. And one key component is environmental sensors. So sensors that detect and see what's around the car. We have dozens of them. So 12 or 16 cameras, for instance, 10 radar sensors and a couple of lidar sensors. It's a typical setup, but also ultrasonic sensors for the parking, for instance. And one very big question is how to develop and especially how to test all the AI, all the neural networks that are involved here to really make autonomous driving a reality on our streets. And one methodology here that really helps is, in our opinion, is data-driven development. And I will present this in this talk. So what is data-driven development? So most autonomous driving companies start with a test fleet. So these are cars that are equipped with prototyping sensors, but sometimes also production-ready sensors that you can also find in your car, in your private car. These test fleet is used to drive around to test software, but also to record data. And this data is then stored locally in the car. And after the test drive, you have to ingest, you have to upload the data to your cloud, to your private cloud, to your public cloud, or to your local data center, wherever you need the data. After this, you have to analyze and to select the data. This means you need a data management because you have hundreds and thousands of hours of test drives you have to manage. Once you have selected the data for different use cases, you have to label the data. This means you have to generate reference data or ground truth data based on this raw data from the test drives. And you need this reference data to train your neural network, to train the AI, and to develop your software. And once you have an iteration ready, once you have your new iteration of your software stack, new generation of your software stack, prior to the next round of the testing this new software on the road, you typically do a validation homologation step in the cloud or in the lab. This is called software in the loop or hardware in the loop simulation testing. Today I will for sure focus on the hardware testing, on the lab testing, because of the hardware interfaces that are involved here, including for sure MIPI interfaces. So and why do you do this? So it's much cheaper to find a bug within the lab or within the cloud testing compared to finding a bug on the street. And you want to be sure that you have found most bugs. Also, not to have any accidents on the roads. Yes, you might have heard of some accidents with autonomous cars, and you really do not want to have this. So this is the reason you want to do as much as testing prior to additional test drives. But once you have released your software stack or your new version of the software stack, you can send it to your test fleet via over-the-air updates in best case. And then, you can start again doing some more test drives, recording more data, and then you can use this new data to develop the next iteration of your software stack. And this iteration here should be very fast. So to accelerate the development of the autonomous driving functions, so this must be efficient and straightforward. So before I go into the details here, maybe some introduction to different sensor architectures we see in cars today and in the future. So most cars today have, at least new cars have front cameras. So these are integrated devices where you have the camera, but also the processing in one housing. The processing here takes the raw data, the image data from the camera, and detects objects, for instance. And these objects are sent to the rest of the car via CAN or Automotive Ethernet, so the standard interfaces we see in the cars today. So this is used for ADAS applications today, but also for some AD applications in the future. But for sure, as I said, we have 12 or even 16 cameras in cars here. We have a lot of surround view cameras. For instance, here a mirror replacement that you see. So small camera modules, and within these modules, typically you just have the imager and not much intelligence, and you just send the data via coax cable, via SerDes connection to your central ECU, to your central processing, where all the sensors, all the radar, lidar, and camera sensors are connected, and where you fuse the data. Another application that is gaining more and more interest here in the community and also in cars is a driver and occupant monitoring. This means the driver monitoring means you want to know if the driver is sleeping, or if he's looking at the road, if he's able to steer the car or not. But this gets wider and wider. This is while in-cabin monitoring is a new state here, a new term, or occupant monitoring. This means, for instance, that you want to have sensors, additional cameras that detect if a child, for instance, was left in the car, and then the driver can be informed via message, for instance. These cameras are working very similarly compared to the outer, the exterior sensors, but typically they work in the infrared domain, near infrared domain. But you have, again, a similar setup with small camera heads and then a central processing in most cases. You have similar architectures, or you see more and more architectures here are also for radar and lidar sensors. This means they use similar setup with our RF transceiver chips, for instance, in a small housing, and then they send the data, raw data via coax cable to central processing. So this is an architecture that we will see in the next years, I think. So, and for sure, MIPI interfaces are involved here in all of this. And now starting with the data-driven development, and as I said, data logging, recording the data is the first step. We have here camera modules that are that have a lens, that have a camera image sensor and a serializer chip. And typically, especially for the surround view setup, they are connected via a long-range sensor interface, a SerDes interface, to a central processing. We have a deserializer chip here, and then all the different chips that are doing the number crunching and executing neural networks. So today we have proprietary interfaces here from TI, from Maxim, or now Analog Devices, and from Sony, and hopefully the MIPI A-PHY in the future as a standard. So, and now how do you record data from the SerDes link? Well, you introduce a logging platform in between the camera module and the processing module. So this means the camera module sends all the data to the logging platform. You have a deserializer, and within an FPGA chip, you typically split the data. This means one data stream is sent to an high-end SSD for storage, and the second data stream is sent to a serializer chip, and then again sent out via coax cable to the processing module. And in best case, both the camera module and the processing module do not even notice that we have a logging platform here in between. So this is an integrated approach where you have all the logging hardware within one box. There's also a distributed approach where you again have the SerDes chips and an FPGA within a now smaller box that can be close to the cameras, and then you send out the recorded data via 10 gigabit Ethernet to a logging platform. And now this logging platform might be might just have Ethernet interfaces, and this can be easier. So this for this connection, we also have an standardized protocol now from the ASAM. This is a CMP, or capture module protocol, that has been released a couple of months ago, and this allows for more flexibility. For instance, this logging device here with the SerDes chips can be from the one supplier and the logging platform from another. So this gives the car manufacturers more flexibility. So what are the challenges here? So for sure, there are high data rates, high sensor data rates, so dozens of gigabits per second, even in a single car. So you have to store this, and you have to store hundreds of terabytes per day per car. So for sure, you need a large and very fast, so high throughput SSDs that are able to store this huge amount of data, not only for a couple of minutes, but for hours and days. And to make life here a bit easier, at least, you can have lossless data compression in real time on the logging platform, so to reduce the bandwidth requirements, but also the storage that you need. And you can do intelligent data selection. This means if you have a redundant scenery you have seen before, for instance, driving on a motorway by night is not really interesting. You might have done this dozens of times before, so you do not have to store the data. So this makes life easier and save SSD storage. So in addition, what are other challenges? So we have the we have already seen the MIPI mass framework in the previous presentation, and for sure we have a lot of advantages here. So all the advanced safety and security functions are really helpful for so the whole homologation process for autonomous driving. But especially here for the logging, but also for the testing, here we have additional challenges, especially due to the encryption and the authentication that is employed. And we see two solutions here. Even today, we just the manufacturer here of the modules is just disabling all the safety and security functions for the test drives, and also for the testing in the lab. For sure, this works, but you have a drawback that you have modified versions of the software both within the camera module and within the processing module, and this is something you might not want. You really want to test the software that is on the road later on. And for sure, this is also possible. You just have to implement all the MIPI mass stack in the logging and in the testing hardware. And for sure, you require good cooperation here with all the companies involved, and for sure, you require the keys for all the encryption functions. So you can have this tapping and this data logging. So once you have finished the the test drives, you want to upload the data and you want to use the data. So the first step is data ingestion here. So what does this mean? So there are generally two approaches to upload this really huge amounts of data. So a straightforward approach is to upload the data directly to the storage. So Ethernet, different Ethernet interfaces here are the standard interface for this. So some users might want to upload the data just to their PCs, to their local PCs. Others want to upload the data to the cloud or to the local data center. But for sure, you need large storage in both environments. If you want to upload using the internet, for sure, you really need very high-speed interconnect, because otherwise it would take days and weeks to upload the dozens and hundreds and thousands of terabytes of data. And this is also the reason why this is a straightforward approach for prototyping and also for research for universities, but only for small data sets. So if you might have only half an hour or an hour of test drive, and if you might have only one test drive per week. So then this is a very good approach. But if you really want to have a large test fleet with dozens of cars and they operating them 24/7, you need another solution. And here, we see in the market that you just use robust SSD modules that can be sent via mail just to the user. So this is also called, or was called, sneaker network in the past. So you need, for instance, your SSD modules that can be handled easily, and then you have a very high bandwidth. Using, for instance, an upload station that can be used on the desk, or you can have an upload station, in your local data center, or even at the cloud provider. So you can also send the SSD modules to the cloud provider, and then the cloud provider can directly upload the data to the cloud infrastructure. So this is really a lot of advantages, especially for larger test campaigns. So now regarding data management, here you see that we have to analyze the data, we have to select the data, and one important topic here is that you have different consumer of the data. So this means you have maybe someone who wants to train object detection. Another colleague wants to validate a lane keep assistant, so lane keeping on a motorway, and the third one wants to validate auto emergency brake in an urban environment, for instance. This means, they have different requirements, different lengths, different durations of the videos, but also so here are some example videos. So driving on a motorway is perfect for the second user here, for the lane keep assistant. Here you have some urban environments, but not that much traffic. But here in the other example, you have much more traffic. So this might be interesting for the first user, but not for the second one. You have a toll station, maybe you have some unexpected, so some motorcyclists, some person who's just passing the street unexpected. So you have a lot of different things that you might to label your data or to mark in your data. And for sure, different weather conditions and lighting conditions, like here driving by night. So this is especially interesting for the colleague who wants to train the object detection. So this means we have a lot of different data, and we have a lot of different consumer of the data that have different requirements. And in addition, as I said before, you also have useless data. So if you do not have any user for the data, then you might be you might want to delete the data. This means that you really want to have a good environment, a good software stack for the data management, to be able to analyze all the data, but also to select the data, so the consumer get the data that they really need and that they can use for their daily work. So once you have selected the data, the next step is labeling. Label the data. What does this mean? So as I said, you need reference data, and yeah, you need to process the data. And one important step here, yeah, this is the latest in this data-driven development, the latest step where you have to do an anonymization. So this is really, there are a lot of different international standards worldwide. But for sure, you have to anonymize all faces and all the license plates in the videos, for instance, due to privacy concerns. So this is really very important, and yeah, you can do this in different steps of the data-driven development. Yeah, latest here in the annotation step. Once you've done this, you might want to do an AI-based labeling. So this means you have you might want to have some 2D, two-dimensional bounding boxes here in this camera image, or if you have a lidar image here, you might want to have even 3D bounding boxes. So depending on the sensor, you want to label here different data. Another thing here is 3D segmentation. So you have, for instance, here you have a camera picture and you want to label each and every pixel to say, hey, yeah, this is a car, this is a road, this is a tree, this is a traffic sign. And this is very helpful input data for the neural network, for the training of the neural network. Yeah, you have to generate this data somehow. And yeah, I just had the example with a colleague who wants to train the lane keep assistant. Yeah, here, for instance, it's totally okay if you just have labeled here all the lane markings, so you can use this for this use case. And yeah, there are at least two ways how to do all this different labeling and also the anonymization. So you can do this manually. So with a really huge workforce of humans that are required here. So this is, yeah, as you can imagine, if you have thousands of hours of test data and yeah, dozens of sensors for each test setup, this is really a lot of work. And this is the reason why more and more companies in the industry are now going into the automation of this annotation. This means that this allows you to really cut the cost dramatically and also to accelerate this. Yeah. So as I said, speeding up this development cycles is also quite important. So the faster you can label the data, the better. So after you have labeled the data, you can use both the reference data and the data you have recorded here. You can use this for training the AI, for developing the software. So I'm not an expert in this. For sure, yeah, hundreds and thousands of engineers and scientists are working on this. And as I said, once you have finalized a new version of the software stack, you can go to the next step. And this is, yeah, testing and data replay in this example here, where you have the validation and the homologation. As I said, today we focus on the testing in the lab with hardware in the loop and data replay. So what does this mean? So as I said, we have the small camera modules, for instance, for the surround view cameras, and now in the lab, as we want to test and to validate yeah, both the processing hardware, but also the software here, all the neural networks running on the processing module. We just remove the camera module and we use the test hardware to insert, to simulate the camera module. For sure, we have to integrate the same serializer that we also see here in the camera module. And we just then send test data we have recorded before we send this test data to the processing module. And this really helps us to test a lot of different sceneries and a lot of different test cases in the lab. So this, as I said, this is much cheaper and also faster than doing test drives on the road. Because, for instance, here, yeah, you can select the test. So, for instance, you found a problem in your algorithms for driving by night, then you can just select the videos, the test data that is labeled with night driving. So you can have a special focus on this, for instance, to really see if you have really solved the bug. So for sure, we have also various challenges here in the testing domain. So one is that we have various sensor interfaces that are used today. proprietary ones, and even from one supplier. The chips are not 100% compatible. So from project to project, you have a lot of manual work here, a lot of adaptations. Also, the register configuration, the I2C configuration is not standardized. So yeah, we have seen in the MES framework, we have a lot of standardization here that would help in the future. But today we have a lot of different configurations here that are project specific. And also a lot of synchronization is required. So if you have dozens of sensors that are connected, all of the sensors have to be synchronized. So this is a challenge for for the vehicle use case for sure, but also for the testing in the lab. So the solution today is to have modular hardware and highly flexible logging and simulation tooling and software, and also, as I said, a lot of engineering that has to be done by test and tooling companies like D-PHYS or by the automotive tier 1 suppliers or also the car manufacturers. So this is a lot of manual work, and hopefully in the future, if we have standards like the MIPI A-PHY, like the MIPI MES, we have much streamlined experience here, so you can really focus more on the testing and not on the environment. Okay, so to conclude my talk, I've presented here the data-driven development workflow with the different steps from the test drives through the data storage and processing and labeling back through the development and the testing to then back to the automotive test fleet. And as I said, it's quite important to have a streamlined experience here and to have short iteration cycles to really make autonomous driving a reality. And for sure, data and data-driven development is a key for this in my perspective. Yeah, thanks a lot.
Great, thanks. Thanks, Grigor. Appreciate it. We do have quite a few questions, and we do have some time in this session. So let's go ahead and try to answer some of these. Just wanted to let everyone know, if you have any questions, please use the Q&A tab on the far right, and the actually it's on this side, on the purple. So we'll go ahead and start answering some of these. So the first, Grigor, do you think automotive MIPI interfaces will be used for lidar and radar sensors? You touched on this earlier, but yeah.
So today for the radar, definitely yes. So we already see the MIPI D-PHYE and the CSI-2. So even this has been developed for the camera use case, we see more and more use of this in the radar domain. Because you want to transfer data with quite high data rates. So the MIPI protocols are really very, very helpful in the radar domain. And also in the future, as I said, you will have distributed radar sensors maybe. There, again, you can use the MIPI protocols, and the protocols are really helping here. So in the lidar domain, so lidar is not that, or is quite new. So we see a lot of different technologies there, and a lot of proprietary interfaces. So maybe like mobile camera interfaces 20 or 25 years ago. But again, here we see more and more D-PHYE interfaces at again, you want to transfer sensor data with high data rates, and the MIPI interfaces are really helping here a lot.
Yeah, that makes sense. And then this one's kind of a fun question, but when do you expect fully autonomous vehicles on the streets?
So a very good question. So actually, we see some autonomous vehicles. So I think in the Bay Area, some autonomous taxis or some test trials with autonomous trucks. I think this commercial vehicles, and especially trucks and delivery. So trucks on a motorway, for instance. So we have a shortage of truck drivers, I think, both in the US and in Europe, and autonomous trucks will really help here. And you have a more or less controlled environment, so autonomous trucks will be within the next years, I think. I think the most interesting question is maybe when will we be able to purchase just a personal car that is really fully autonomous? Maybe, I don't know, maybe within 10 years. So the question is really the price, because for some commercial applications, the sensors can be quite expensive, so processing power can be expensive. But for a private car, you might not want to spend that much money.
Sure.
Yeah.
Yeah, fair enough. Yeah. Actually, I'm presenting in the next. Sorry to pitch my next session, but what we're dealing with autonomous driving as well, and it is a question, right? Is when will we see it? Not just in commercial or industrial is different, right? Than consumer, right? And there's a clear deviation there right now. There are some other kind of more technical maybe questions. We can try to address some of these. So if you use lossy data for the training, how do you know the row data will give you the same tag?
So this is a very good question, and so different customers, the different players in the industry have different answers for this. So I think most say we do not want to have a lossy compression because of this, because you are not sure, do not want to train your neural networks on some compression artifacts. So this is the reason why a lot of companies are asking for a lossless compression. So for sure you have some drawbacks. So you can save only, I don't know, half of the storage, and not 90% of the storage. But a lot of companies are going for this. But again, some say no. My neural networks are working fine with compressed data, so we can use, for instance, the standard video compression algorithms we see in the industry. We use on our TVs and on our laptops. And we are totally fine with this. So the key again here is that we have, as a tool provider, has to be flexible and have to offer both.
Makes sense. There's a couple of questions related to the FPGA that you mentioned earlier. Not sure which of these we can answer, but there's a question: which part did you use, or are you using?
So these devices here are just an example, but so I can give you really more or less industry-wide answer on this, because we have a lot of Xilinx FPGAs, because Xilinx FPGAs are quite good regarding the MIPI interfaces. They have good support for the D-PHY. So a lot of these devices are using the latest Xilinx FPGAs, including our platforms. But
and then how much is there extra latency that's introduced by using this kind of FPGA?
Sorry.
What is the extra latency, or is there extra latency introduced?
So it's minimal. So we had done some measurements here, and most of the latency is due to the destabilizer and stabilizer chip, and the latency within the FPGA, it's in comparison, not that important.
Sure, fair enough. And do you see, so to kind of shift gears a bit, do you see RGB IR being used, and in your opinion, is MIPI prepared to handle this?
We have seen that, but to be honest, in most projects, it's not that important how these format looks like, because we receive the data, we store the data, and also for the testing, we just go the other way around. For sure. So we have other solutions where you have synthetic data, where you have like a computer game, like a simulation environment. There we have the possibility to do this, and this is also employed industry-wide. But for this use case, it's really not that important how really the image sensor looks like. So if you have RGB or black and white, RCCC, whatever color pattern you have here, or even infrared.
Sure, thanks. A lot of interest in this FPGA. What's the clock frequency used in the FPGA? Share.
So this really depends. So I mean you all know the frequencies here of the D-PHY. So you have standard applications today, you have up to 6 gigabits per second. So this is a quite high data rate, and if you can imagine, you have 12 or 16 cameras with this high data rate. yeah, for sure, you have to work out how you process the data and how you transfer the data.
Yeah, sure. And then I think a follow-up question: what about fault tolerance detection in the sensor stack? Is that, yeah, that's the whole question.
So this is like for the testing, the question is simple. Yeah, so we just do not have to trigger all to trigger all these functions. Yeah, as I said, we do not want to be visible in best case for for the processing module. But if we go so if we go here, so in this kind of testing, for sure we first of all, we start with the project. We want to have everything up and running in best case, and then for sure we want the customer ask us to trigger all the different mechanisms. Yeah, so each and every check you do here in the processing module in the software, you might want to trigger the check by the test. Yeah. So
sure.
Yeah, so depending on the requirements, for sure, this can be implemented in the tests to not only test the algorithms, but also the safety functions.
Great. Yeah, fair enough. I think we got through all the questions. There's no other questions. We have a couple minutes left. Is there anything else that any other thoughts or anything else you want to leave us with as we, we've definitely seen an increase in, MIPI for automotive, right, over recent years. And we say it as well, like CSI-2 really is the de facto standard.
Yeah.
Why do you think that's been the case?
Yeah, so this, I can really give a comment on this from an engineering perspective. So so for this this communication link here, as I said, MIPI D-PHY and CSI-2 is used today. So in really each and every project in the camera domain, like 99.9% of the projects are D-PHY. And this is really helping, because in the first projects, like when I started in this domain like 6 years ago, we had only we had some projects with some proprietary LVDS, and then you had some timing, you had to debug the timing, you had to really go into the details here, and this is not required anymore. So now we have a D-PHY implementation that follows the standard. So in our test equipment, but I think this is also the case for all the companies who are developing the camera module, the processing module, and so on. Yeah, so you can just use it. There's a standardized interface. It's the same interface in all projects, and this is really helping a lot. Yeah, so this makes really life easier.
Sure. And you mentioned a lot about D-PHY. Are you seeing any C-PHY implementation?
To be honest, not yet. No. So we are waiting for this, but at the moment, there are some C-PHY support in some serializer and especially deserializer chips. Because here, if you have connected 4 cameras, for instance, then you might require, I don't know, 2 or even 4 D-PHY channels, and you might replace this with a higher bandwidth C-PHY channels. Yeah, so here there are some C-PHY implementations, I think, but in most projects, just the D-PHY is used, because also in the image processing hardware, the different SoCs and FPGAs and so on, we see just the D-PHY interface at the moment.
Great. And I did see one more question come up. We only have about 1.5 minutes left, but will A-PHY be applicable with ALP or legacy state machines, or both, and any key factor to decide which to go ahead?
Good question. So as I said, we have a lot of different different sort of links here at the moment, and so for sure in the first project, MIPI A-PHY will be just another one, but and we will support all the components that we have implemented till today. But for sure, starting from the second project, we will gain a lot of simplification, and we will gain a lot of benefits from the A-PHY.
Great. Yeah. Great. Well, I think that about wraps up our time today. Really wanted to thank you, Grigor, for taking the time to present today. I think it's very interesting, and it really ties well into our theme for this first part of the day about MIPI and automotive. So with that, I want to thank everyone.